underground reservoir, for instance, or any body in the space, doesn't matter. So you have a body in the space, it could be underground reservoir. If you have sort of gravitational field of this, someone could tell you, you have mechanisms that you can measure the gravitational field. Could you say that this body is, what is the shape of this body? Now, if you take a sphere, if you take a ball, so you know what is the gravitational field of this. What's the great gravitational field of a ball? That's x over length of x, the modulus of x. So the gravitational field of a ball, if you look at this, let me look here. Take any ball. So gravitational field is, let's call it vector field, gravitational vector field, is minus x over x. It goes in this direction, 3 dimension. It goes in this direction. Okay? And you realize that this somehow can be put in here. Although it's not harmonic, but you can actually play around with this. And the question is whether the gravitational field given to you will tell you that you get the shape of this exactly, or it can be two different shapes. So let's say uniqueness is the question. So if the gravitational field of a body, of another body, is going to be this, is that going to happen? Or that body you're giving me has to have the shape of a ball? So for geophysicists, this was an interesting question in the sense that if you get gravitational field, you sort of know the shape of the body, approximately. And there are not two different shapes giving the same gravitational field, because then it means that you have guessed the wrong picture, because you don't see the underground reservoir. So if you could make an intelligent guess by a computer or whatever, and that would be the shape of it approximately. There would not be something else which is like this, and you miss that part of the reservoir. Okay? So if you want to extend this to the concept of gravity equivalent bodies, is the following, that we can actually replace this. Okay, let's rewrite this. Let's go back here. If you rewrite this, this is going to be a constant. This is the constant. Let's call it CR. And then you have the harmonic function integrated with respect to a measure. And that measure is CR the arc mass at the point Z. Agree? So I can rewrite this as integration of the harmonic function with respect to this measure. And that measure is exactly the Dirac mass up to this constant. And then I'm going to get the stack. I'm just rewriting, I'm not doing anything. So this means that, given that source, so given a measure, we say omega containing support of the measure is a Quadrature domain with respect to the measure if the integral over omega equals the integral of this with respect to the measure. So the picture would be something like this. And this is the measure. So if you, given the measure, if you can find a domain omega, which contains the support, and that integral identity holds, we will call the domain a quadrature domain. So quadrature domain with respect to harmonic functions, we call it HL1 omega. Harmonic functions. Integral harmonic integrable functions. I can do the same because I know that I also have, if this is not harmonic but subharmonic, so the subharmonic one goes like this, yeah? Or this one. This is the subharmonicity. Okay? So if I have subharmonicity, I can do the same here, and I will call this subharmonic partial domains, or for a different class, for subharmonic SHL1 here, if you want to denote it like that. If you get the integral of subharmonic functions, dx over omega is larger than or equal Sx measure. S is subharmonic. Laplacian S is larger than or equal to 0. If you have subharmonic functions, and then you know that this is going to be inequality, and a similar version we can actually define like that for subharmonic ones. You're still thinking, what does this have to do with obstacle problem? So let's try to link that. Okay. Yes, you're right. This is more close than I thought. Yeah. Yeah, this is actually interesting now because the question of sign comes in also, which is interesting. Now, think of functions that are harmonic. So take, for example, you take harmonic function, which is x minus, let me put it like this, hy is x minus y to the power 2 minus n in dimension n, larger than or equal to 3. Harmonic. So let's say omega, a partial domain for the class HL1 for some measure. Suppose this is a partial domain for some measure. Then this is going to be harmonic when x is not in omega. When x is here, this function is of course harmonic because y is here. So when y is in omega, x is not in omega, they never meet, and this function is harmonic. Agreed? It's a harmonic function. So the integral of x minus y to the power 2 minus n d of y over omega equals the integral of x minus y 2 minus n d of the measure for all points x outside. Points have to stay outside. So what happens here is that we can actually look at this function. Look at the function u of x being the difference of these two functions up to a constant, some Cn, x minus y, 2 minus n, over omega dy minus x minus y, 2 minus n, the measure. I'm taking the difference, and I'm letting x to be now inside, and I know that this satisfies that Laplacian of u is because I'm putting a normalized factorial of the characteristic function of omega minus the measure. It's just computational. You get this, and then because of this, once x goes to the boundary, x is not in omega anymore, then u is going to be 0, and also gradient of u, we can prove, is going to be 0. You recognize this now, like the obstacle problem. But omega here is not defined by u is strictly positive. So that is already a big problem. So if you want to apply the theory you just had, you cannot do that. You have to develop that theory further in order to be able to solve this problem. So this is called quadrature domain, and then my motivation even to come into free boundaries was actually originally from here. So locally, away from the measure, when you don't see, we have Laplacian of u plus characteristic of omega, and u is 0 in omega complement. So you can actually write this problem differently. That is, Laplacian of u is characteristic function of u is not 0. That's a lot of differences between the obstacle problem and this problem. Now u also changes sign. So this was open until around 2000. In dimension 2, Sakai proved a lot of things about this in 91. And then until 2000, sometimes 98, 99, this was completely open. And then at that point came some results also, with machinery of monopolistic formula, etc. You could completely prove it. So that's the connection between problems that are coming from geophysics in vacuum with gravity equivalent bodies to connect it to an obstacle problem in a little bit more advanced setting. Okay, I think I will finish here. Let's take a break, and then now and then we try to do a little bit of exercises that's suggested. Then we formalize it on the board. Those exercises we have suggested. We can formalize it. Yeah, this was a little bit sidetrack, but I wasn't that this week. Because numerics wouldn't be a problem. Because not many of you are doing numerics,